Hi, the purpose of this video is to give you a sense on to deal with um, homework one problems. The gradable part of this homework will be available later. For now, I'm just throwing prompts at you that you should be working on. It's beginning of week 3, which means that chapter 1 should be nearing completion and you should be starting to acquire knowledge for chapter 2. So, chapter 1 homework, as in the problems you should be doing and you should be getting familiar with, has 31 problems, and I am going to build a sketch on how to do those problems. There will be some um, more or less complete solutions, but I wouldn't um, expect all of it to be alpha and omega. Some questions will be skipped, or I will just tell you how to do it rather than actually doing it. So, again, this is spring 2020 um, statistics homework one set of problems. So, let's take a look at problem number one. Problem number one has 5 parts. The first part says, what is the probability to select a 10, a queen, 4 of hearts, or an ace of spades? So we're looking at it as probability of picking a 10 or a queen or a 4 of hearts or ace of spades. Well, there's how many tens? There are 4 tens in the deck, there are 4 queens, there's only one 4 of hearts, and there's only one ace of spades, which comes out to be 10 out of 52 or 5 out of 26. There is not much else to it. Again, part B, there's sum of 6 appears in a single toss of a pair of fair dice. There's a couple ways to start it. One of the easy ones is if you make a matrix of all the possible tosses of 2 dice. You can very easily count how many of those will give you a 6. So 1 and 5 will give you a 6. 5 and 1 will give you a 6. 3 and 3 will give you a 6. Anything else? Yes, no, maybe. Well, that's it, right? 1 and 5, 5 and 1, and 3, and 3. That gives you a sum of 6. Again, you cannot have a 6 because 6 plus 1 is 7. So that's 3 out of, well, 36. So that's 1 out of 12. Question C. We're looking for non-defective decks of cards. There's 18 defects in 750 decks. So what we're looking for is 1 minus probability of a defect. Well, 1 minus probability of probability of defect. So that equals to 1 minus 18 divided by 750. Right, there's 18 defects in 750. So this is observed probability. And there is that. So that that should come out to about 3 in 125. Right, so 1 minus 3, which is 122 divided by 125. Right, again, we're looking for non-defective decks of cards, so we're looking at this difference. Another way to think about it is that's all the non-defective cards divided by all the decks, which is again the same thing. All right, the 9 or 11 comes up in a single toss of a pair of dice. Well, again, we can look at our little matrix. To get 11, we need 5 and 6, and 6 and 5. And to get 9, we need 5 and 4, 4 and 5, 3 and 6, and 6, 6 and 3. 1, 2, 3, 4, 5, 6. Right? So it's 6, 1, 2, 3, 4, 5, 6, divided by 36. Right? Because this is probability of 9 or 11, which equals to probability of 9 plus probability of 11 minus probability of 9 and 11. Since 9 and 11 cannot happen at the same time, we don't have to worry about them in the addition rule. Probability of 9, again, it's 4 and 5, 5 and 4, so 2 out of 36, and then 11, 5 and 6, 6 and 5. Am I saying it right? No, 11 is 2 out of 36. 9 is 5, 4, 4, 5, 4, which comes out to 6 out of 36. All right, so this is question 1. One more part, E. All right, so part E, at least one head appears on 3 tosses of a fair coin. Also, question is, what are the possibilities? Well, there's tail, 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 head, tail, head, tail, 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 head, 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 tail, head, tail, head, and tail, head, head. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's the 6 possibilities, and we need at least one head. This one, this one, this one, this one, this one, this one, this one. 7 out of 8. And that's it for question 1. All right, question 2. Question 2 is sounds complicated, but what I want to see as an answer is just simply written out what this means. It means that we're looking for a probability of picking a jack as a first card and not picking a jack as a second card, right? This is a complement, so there's everything but a jack on the second. And in a single trial, I mean in a single dealing of 3 cards. So question 2 is just asking for a sentence, and we're not going to worry about it just yet. It's easy enough to figure out. Question 3. Question 3 is one of those fabulous questions where you have a container that contains a collection of or a number of items. In our case, we have red, green, blue, and yellow marbles, and we're asking for finding probability. So probability of yellow or red. Well, so this is probability of picking a yellow plus probability of picking a red minus probability of picking a yellow and a red. Since none of our marbles are double colors, we're just looking at probability of one plus probability of the other one. Yellow is 18 out of 60. 20, 30, 40, 50, yeah, 60, plus red, it's 8 out of 60. So that comes out to about 26 out of 60, or 13 out of 30. Part B, not red or blue. Well, so probability of not red or blue. Not red is everything but red. So in our case, that's 60 minus 8 divided by 60. Plus blue, and there's 22 blues. But not red and blue have an overlapping section, and the blue ones will overlap. So if we're looking at all the marbles but the red ones, blue ones are included. So what we need to do here, instead of just doing not red plus blue, we need to do minus not red and blue. And the only marbles which are not red and blue are blue marbles. So this comes out to be minus 22 over 60. So you should get an answer of 52 over 60. Which is 13 by 15. Question C. Not yellow. So probability of not yellow. Well, how many yellows are there? 18. So that's 60 minus 18 divided by 60. That's 42 out of 60, which comes out to be 7 out of 10. D. Green ones. Well, probability of green, that's an easy one. That's 12 over 60. So that comes out to 1 out of 5. And there's part E. Part E is red or green or blue, which means probability of green plus probability of red, order doesn't matter, probability of blue. And again, since there is no marbles which are two color ones, this doesn't have to have the the removal of double counts. And so they write blue. Okay. So green ones, we have 12 over 60 plus probability of red 8 over 60 plus probability of blue 22 over 60. That's 30, 42, 7 out of 10. The other way one could look at it is, this is all the colors but yellow, so this is 1 minus probability of yellow. And what is 1 minus probability of yellow? Well, that's probability of not yellow. And that's why E and C have the same answer. They're asking the same thing. And that's question 2. sorry, question 3. Question 4. Question 4 is actually similar to question 3 with the difference that this was addition rule. Question 4 or problem 4 is multiplication. And multiplication rule looks the following. It's probability of A and B equals to probability of A times probability of B given that A. Right? So we draw one marble and then we draw the second one. In problem 4, because we have replacement, events B and A, drawing the second marble is independent, which means that the probability of B given that A equals to probability of B, which means that our formula for this question is simply that. Alright, so both of them are green. Well, so a probability of both of them being green, so which means we're picking green and green. 12 out of 60 times 12 out of 60. It should come out to 1 out of 25. Again, I really like fractions because fractions tell me how you got there. I'm okay if you decide to do decimal places. Again, fractions, there's nothing wrong with fractions. So if you're good with fractions, use fractions. Otherwise, I'll take what you can give me. All right, B. First one is red, second one is green. Well, again, red is 8 out of 60 times what? Second one is green. That's 12 out of 60. And that should come out to be 2 out of 75. All right. C. Neither one is yellow. Well, so we're looking at not yellow, and then again not yellow. If you look at problem 4 and problem 3, you'll notice that it's the same number of yellow, blues, greens, and reds. And we know what the probability of not yellow was. Right? Which means that probability of not yellow and then again not yellow is going to give us 7 out of 10 times 7 out of 10, which is 49 out of 100. All right, moving to the next one, D. D is neither are red or green or both. Well, they cannot be both, so we're looking at something that is not red and not green. So probability of not red or not green is equal to what? Well, that's equal to 1 minus, well, probability of red is going to be 8 out of 60. Probability of green is going to be 12 out of 60. Right? Red, probability of just picking red would be 8 out of 60. Probability of green would be 12 out of 60. And we're looking for the not part. Not red or green. Am I doing this right? I think so. either are red or green. So they can be only blue and yellow. Blue or yellow. Let's see if we can do it. That's 18 plus blue 22. Okay. All right. So we get the answer both ways. Right? Either we do 1 minus those not red or not green, and that gives us 40 out of 60, or we're just looking at blue and yellow, and again that's 40 out of 60. So we're looking at both, so that's going to be 4 out of 6 for the 40 out of 60 for the first one times 40 out of 60 for the second one. So that comes out to be that's 1/3, 2/3, 4/9. That looks about right. For blue or yellow? Yeah, I think so. Sorry, it's late. I spent my weekend fixing my PC, so unfortunately my brain isn't at 100%. All right. Next one, E. Second one is not blue. Well, probability of not blue is 1 minus probability of blue, which is 22 over 60. So this comes out to be 38 out of 60. So that comes out to be 19 out of 30. F. The first one is yellow. Again, because we're doing replacement, I don't care which one we were picking, because the first one is going to get put back in. So when I ask you about the probability of just the second one, nothing is affecting the second one. Because of the replacement, the two events are independent. So in case of F, I'm just looking at the first one. So again, this is 18 out of 60, and we are done. 3 out of 10 if you prefer. G. Excuse me. G. At least one is blue. At least one has a really cool complement. The complement of at least one is none. So when I say at least one is blue, means I either want one blue one. Again, I draw two marbles, but one blue one, plus probability of two blue ones, or I look at this and I say, hey, I can look at the complement of that. And the complement of that is 1 minus, well, none. 0 blue. And what does mean 0 blue? Means I don't draw any blue in the first or the second one, which means I don't draw a blue on the first and on the second time, right? 0 blue means no blues. And what does mean no blue? No blue means 38 out of 60 on the first and 38 out of 60 on the second one. which should come out to 38 times 38, 1444 divided by 3600. So 361 divided by 900. So probability of not picking a blue and not picking a blue. Probability of 0 blues, right? So we get this. Now again, we have to deal with this 1 minus. So now we're doing 1 minus 361 divided by 900. Again, what we just calculated is this. Rather than making one calculation then a second one, I just looked at one of them. And that comes out to be 539 divided by 900. Okay. So at least one, when you get something that says at least one, means 1 or 2 or 3 or more. It might be easier to just look at the opposite of it, which is none at all, right? If you're going 1, 2, 3, 4, 5, the opposite of it is 0, since we cannot have negative. So I could look at a drawing of 2 marbles where one of them is blue, and I could look at the drawing of 2 marbles where both of them are blue, or I can look at the complement of that, right, of not picking blues at all. And if I say no blues, no blues and no blues, I get 38 out of 60 times 38 out of 60, which comes out to be 361 out of 900. But this only gives me this part. I still have to account for that one, and that one is accounted for here, right? Complement of it. All right, moving on. At most, one is red. And again, at most, one red means 0 red or 1 red. And we're drawing twice, which means that this sounds like a complement of 1 minus 2 red, right? 2 red being a complement of 0 and 1 red. At most means 0 or 1. So what's the probability of picking a red? Probability of red equals to 8 out of 60. So probability of red and red is 8 out of 60 times 8 out of 60, which comes out to be 4, 8 times 4 out of 225. So if red and red is 4 out of 225, then 1 minus probability of 2 reds, 1 minus probability of red and red equals to 1 minus 4 out of 225, which comes out to be 2 to 1 over 2 to 5. How big is this? Hopefully this is sharp enough. Sorry about the jiggle. Making sure my camera is sharp enough. Still struggling with the computer not behaving the way I want it to behave. Alright, so this is H. Let's look at I. I says the first one is green, the second one is not. So again, we're looking for probability of green and then not green. Well, probability of green is 12 out of 60 times probability of not green. That's 60 minus 12, not green, divided by 60. Which comes out to be 4 out of 25. So probability of green, not green, probability of green is 12 out of 60, probability of not green is 48 out of 60. You multiply it because and means multiplication rule, comes out to be 576 over 3600, and that simplifies to 4 over 25. And then J is what? Only one red. Well, so that's probability of red and not red. Because the events are independent, it doesn't matter if I take the red first or I take the red second and the non-red second or first, respectively. So probability of red 8 over 60, probability of not red 52 over 60, and that should come out to be 416 over 3600. That should come to be 26 over 225. Super. That's problem 4. Problem 5. Problem 5 gets a little trickier. And the reason why it gets a little trickier because now we don't have replacement, which means we're redoing all those calculations, accounting for the fact that when we pick the second marble, there is less marbles in the jar. Let's see. So what was this first one? First one was how do we make let's make some space here. The first one was green and green. So 5A we're looking at green and green. So that's 12 out of 60 times 1 less green, so there's 11 out of not 60 but 59, right? Because I took out a marble out, and it's 59, and I took out a green marble in particular, which means that this becomes 11. And that comes out to be 11 out of 295. Again, the numerator gets reduced by 1 because we took out green marble out. The denominator gets reduced by 1 because we got rid of a marble. Alright, B. B is... what was B? B was... first is red, second one is green. Well, first one is red, 8 out of 60, times second one being green. There's 12 greens, but there's only 59 marbles left. C was, neither one was yellow. And there were 42 yellow ones, and then we lost another non-yellow, 41 out of 59. D is neither red or green, or both. So we got that neither green or red, which came out to be 40 out of 60 for the first one, and then 39 out of 59 for the second one. E was, the second one is not blue, which means we don't care what the first one was, so the second one, not blue, there's 22 blue ones, that comes out 38 out of 59. Again, why 59? Because it's the second marble. We drew a marble out before we went for non-blue. How did I get that? 1 minus 22 over right? 1 minus over 59. Not blue. Alright, so that was E. Let's look at F. F was, the first one is yellow. Well, how many yellows were there? There were 18 yellows. So it's 18 out of 60. Number F, G. At least one is blue. How did we do at least one? We went for a probability of none. So the first one was 38 out of 60. And then we lost one that isn't blue, right? Because we went for blue and blue. So that's 37 out of 59. G, H. H was at most one red. So we're looking at 1 minus the probability of 2 reds. Oh, we have to finish G. Right, so that was the first, and then we had to go 1 minus that. Sorry. Yep. Not blue, not blue. Multiplication and then 1 minus. Okay. H. At most 1 red, so 1 minus 2 reds. So it's 1 minus 8 over 60 for the first red and 7 over 59. Should be 59. For the second red. H. I was, the first one is green, but the second one is not. Green was 12 over 60, and the second one, well, we took only a green out, so there's still 48 non-green ones, but there's one marble less. And then finally J was only 1 is red. Well, so it's 8 out of 60 times 52 over 59. Now, it doesn't matter if we take the non-red first, because we are still doing multiplication, so we can switch the top. So 52 over 60 times 8 over 59 is equal to 8 over 60 times 52 over 59. And that completes question 5. Question 6. Again, same thing. Yellow and blue marbles finds the probability without replacement. Both are blue. So this is 6A. Both are blue. Well, first blue is 2 out of 5. Second blue is what? Well, it's 1 out of 4. B. Both are yellow. Well, 3 out of 5 times 2 out of 4. Right? This comes out to be 1/10, and this comes out to be 3/10. And then C, 1 is yellow, 1 is blue. Okay, so that's 3 out of 5 times 2 out of 4. Am I saying it right? 1 is yellow, and that's 3 out of 5, and 1 is blue, times 2 out of 4, and that comes out to be 3 out of 10. So this is blue, blue, yellow, yellow, and this one is yellow, blue. And if we go blue, yellow, that's going to be 2 out of 5 times 3 out of 4. And still going to come out the same. Alright, 7. Probability of drawing 3 aces at random from a deck of 52 cards. Well, how many aces are there? 4, right? So the first ace is going to be 4 out of 52. And then you replace, you put the ace back, so there's still 4 out of 52 times 4 out of 52. And that's the first one. Second one is without replacement. So first card out of a whole deck is still 4, because there's still 4 aces. But then we try again, there's only 3 aces left. And it's 52 No, it's 51 because we took both an ace and a card. And then finally it's 2 out of 50. So this comes out to be 1 out of 2197. And this comes out to be 113 times 1 over 25 times 3 over 51. So that's 51 times 25 times 13. 3 out of 16,575. All right. Question 8. Ooh, question 8 is very similar to one of the lecture questions, but there's a little caveat. We know if at least one child in a family of 3 children is a girl, what's the probability of that all children are girl? There's a little caveat. We know that one kid is a girl. So when we write out all our possibilities, and that's boy, 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 girl, boy, girl, boy, girl, boy, boy, 3 girls, girl, girl, boy, boy, girl, boy, girl, girl, which is the 8, right? We know that there's at least one girl, which means that 3 boys are out, which means that we have 7 choices. And how many of them are all 3 girls? 1. 1 out of 7, not 2. 1 out of 8. So you gotta be careful about those little things. So when it says at least one kid is a girl, the one which has all boys has to be thrown out, which means 1 out of 7. All right, next one. Problem 9. Problem 9 is tricky and one has to consider. So we have 2 boxes. This one has 4 black ones and 3 white ones. This one has 6 black ones and 2 white. And we take one and we put it in here. Right? Which one? Well, we don't know. So we can describe this mathematically and we can say, hey, 4 out of 7 times, right? 4 out of 7, we're going to take a black one and put it in here. And if we put a black one in here, we take a black marble here, we're going to have 9 marbles, 1 plus 8, right? 9 marbles. And we're going to only have 2 white ones. That's option number 1. We take a black marble and we move it to container 2. The other option is we take a white marble and we move it over. What are the chances we're going to pick a white marble? 3 out of 7. So what happens in the second one? Well, now we have 9 marbles here. We had 8 plus 1 white one. And we have 3 white ones. Now, which option are we considering? Well, how about or? Either this happens or this happens. Both of them cannot happen at the same time. Which means addition rule. So what we're looking for is 8 out of 63 plus 9 out of 63, which comes out to be 17 out of 63. Again, the problem looks scary, but if we split it up, what happens if I pick a black marble? What happens if I pick a white marble? And either this or this happens. And in our case, addition rule. And since we cannot pick a white and black marble at the same time because we're picking only one, ta-dam. 10. 10 is easy. You just have to draw the tree diagram. 3 heads, 3 tails, 2 heads, and whatnot. So I'm not going to do it because that's easy to do. Plus, if you did the boy-girl, this one is a freebie. Question 11. How many ways can 3 different coins be placed in 2 different purposes? So, let's call it bag 1 because purse is too hard to spell. Bag 2. Tricky part about this question is it talks about 3 distinct or different coins, which means coin 1, coin 2, and coin 3 are different, which means that you have to deal with this somehow. So I'm going to say that I'm going to take coin 1, 2, and 3 and put them in bag number 1, which means I don't put anything in bag number 2. Or I could put coin 1 and 2 in bag number 1 and only 3 in bag number 2. Or I could put 1 and 3 here and 2 here. Or I could put 2 and 3 and 1 here. Okay, I could put also 1 here and then 2 and 3 here. 2, 1 and 3, and 3, 1 and 2. Or I could put all the coins in bag number 2. So what are our options? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 ways. There's 8 ways to put 3 different unique coins into 2 bags. And those are all the possibilities. Again, a little tricky if you were expecting a math problem rather than a thinking problem. Very doable if you put yourself in a position of like, I don't know what to do it. Let's write it out. Let's do a little diagram. At least for me, those little diagrams are very helpful. If you find them helpful, great. If not, you're gonna have to find another way. If you're still struggling with it, let me know. I'll find another way to deal with it. So it will make sense for you. Question 12. 5P3. This is this and question 17 are 2 calculator questions. Questions, do you know how to use one of those and which buttons to push? If you have one of those TI X30 XSII calculators, you might find this NPR button under PRB. So there's a button called PRB, and if you click that, you will find NPR and NCR and exclamation point there. If you have one of the older calculators, you will see the NPR and NCR and exclamation point somewhere on the face, and you have to go second shift. If you have one of the big scary monsters, they're hidden under the math button. So you hit math and then you scroll over to probability. So math and then probability, shift over around. So every calculator has. If you have a calculator that you like, don't know where the button is, post it on Laulima and I'll pull up the instruction manual for the calculator and find it for you. So 12 is just plug and play. All right. Question 23. Find probability of scoring 8 points on 2 tosses of fair dice. Well, we did that. We did the matrix for fair dice. So how do we score How do we score? No, hang on. Where are we? Did I lose myself? No, problem 14. Okay. 8. How do we get an 8? Well, 5 and 3 will give us an 8. 3 and 5. And then 4 and 4. No, hang on. Where am I? Am I talking? Oh, sorry. I'm looking at the wrong paper. Troubles. All right. 14. In how many ways can 8 books be arranged on a shelf? We're going to come back to this one. 8 books can be arranged on a shelf. Any arrangement. So if we have 8 books, 1, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, and 8. And we have 8 books to be arranged in here. This is a very standard question of 8 factorial. Right? We have 8 unique objects placed in 8 unique spaces. 8 factorial. Or, if you prefer, you can try using this and it'll be 8p8, which will come out to be 8 factorial. Problem B. Problem B is slightly different. 1, 2, 3, 4, 5. 1, 2, 3. We have some, if you're old, ancient even, you used DVDs or, DVDs. And if you had a set of DVDs, you had a set of 8 movies placed. But some of those movies came in a box set, which means that those 3 particular DVDs need to stand together. So you have 5, 2, 3, 4, 5 standing apart, and then you have this weird 6th one which has all those cassettes standing together. Or if you're super old, you bought books, right? Novel number 1, novel number 2, and novel number 3. So what you're really arranging here in B is you're arranging 6 unique things in 6 spaces, because this segment is going to be moving around as you arranged. Of course, we have to account for the fact that books A, B, and C can be arranged differently. So those three books can be also arranged depending on how you like, which means that we have to account for the arrangement here, and that's 3 factorial, right? So 6 factorial talks about the whole bookshelf, where 3 factorial just talks about the arrangements of the books in this set that need to stand together. C is very similar, but C has a special place at the beginning. 2, 3, 4, 5, 6, 7, and 8. One, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6. Right? So again, we have this kind of setup. Now here, these 2 books aren't moving around. They're here, stuck at the end. So what we are rearranging is the 6 factorial of the books in the middle. And now we just look at those 2 books. It could be AB or BA, which means that there are 2 possible arrangements, right? 2p2 is 2 factorial, which equals to 2. So that's that, right? So what we're looking at is we're looking at the 6 in the middle, because those 2 are stuck on the edges. And then we're just checking if it's, which way it's arranged, this way or this way. So that's 14. All right, that page is done. 15. Problem 15 or question 15. Question 15. How many numbers consisting of 5 different digits each can be made from 1, 2, 3? So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the number must be odd. So we have 1, 2, 3, 4, and 5. And this one, this number as a whole needs to be odd. Well, what's an odd number? Odd numbers are numbers which have the last digit being odd. So let's start with the unique one, right? When you have a problem like this, you start with the unique pieces of it. And in our case, this last place is important. It has to be odd. How many choices do we have for an odd number here? Oh yeah, sorry, I'm talking to myself. Well, there's 5 choices here, right? Because it's 1, 3, 5, 7, and 9. So there's 5 choices in here. How many choices are left? Well, there were 9. We took one of the odd ones. So what's left for the first one? There's 8 choices here, 7, 6, and 5. So this is 5 times 8p 8p4. That's the solution. Again, start with the odd one. See how many, odd one. Start with the unique one in the setup you currently do, right? Bookends here, set here, odd digit here. Start with that one. See what are the choices there, and then look at the rest. In our case, we use up 1 digit here. We have 8 left. Why? Because they cannot repeat. And that gives us the rest. Alright, B. The first 2 digits of each number are even. Okay, 1, 2, 3, 4, and 5. This has to be even. How many even numbers do we have? 1, 2, 3, 4. So the first choice is 4. There's 4 choices for the first digit. Second digit, there's 3 choices for the second digit. Why 3? Because we used one of the even digits already here. And then what's left here? Well, there's 7, 6, and 5, which is 7p3. And that's the solution. This comes out to be about 8,500. This comes out to be about 2,500, give or take. Again, I'm fine with this, or I'm fine with you actually multiplying it out. And that's question 15. Oh, I'm leaving stains on my desk. Oh well. Question 16. So what do we have for question 16? How many ways can 3 men and 3 women be seated at a round table? Alright, so imagine a round table. 1, 2, 3, 4, 5, and 6. No restrictions are imposed. Well, the thing about the round tables, which we might not realize, and for people that ever planned a wedding, this is easy, but for the rest of us, if you consider this table, how many people do I need to arrange? I need to arrange only 5 people, because the 6th one is going to go into the place that we have left, right? Because if I arrange those 5, the 6th one has to be here. If I arrange those 5, the 6th one has to be here. So what am I arranging really? If there's no restrictions, I'm arranging 5 people into 5 unique places. And the 6th one is just going to go where it needs. Part B. 2 women must not sit together. mother-in-laws shouldn't sit together at a wedding. Well, if two women cannot sit together, what are the options we have? Well, let's take a look. So we have one woman here, and the other one could be sitting here. We have one woman here, and the other one could be sitting here. And then the last case is one is sitting here, and the other one is sitting here. It cannot sit here because this is the sixth space. Right, so those are the three arrangements. Check. Now we have to sit all the other people. Which other? Well, there's 4 other people to be seated. And that's 4 factorial. Right? So we have 3 arrangements for the odd setup, which is the 2 particular women, and then the rest of it needs to sit somewhere around. And then finally C, each woman is to be seated between 2 men, or each man is sitting between 2 women, which means that we have a setup that looks like this. So let's look at it. Let's say we seat men with numbers 1, 3, 5 and women with 2, 4, 6. So one of the possible arrangements is 1, 2, 3, 4, 5 and 6. Another one would be what? How can we arrange it differently? We could rotate it, right? But then they're sitting in the same configuration, just shifted. So how do we do it? We could, again, consider that what we are really asking in those arrangements is 3 and 5. So 1, 2, 5, 4, 3, and 6. Right? I switched these two. Then those are 2 different arrangements. Right? Okay, what else can we do? Well, we have to arrange not only the women, but we have to arrange the 3 men. And if you arrange 3 men, that's 3 factorial. Right? So one arrangement is I'm switching 2 women. I'm anchoring everything at 1. Now, the reason why I'm anchoring everything at 1 is because let's look at this. Because this arrangement and this arrangement and this arrangement, all of those are the same arrangements. I'm just rotating it around. So by anchoring one person, number 1, in both cases, I'm going to be shifting things around here rather than just doing this twisty motion around. Right? So by anchoring 1 in both cases, I get to play with the other 5. And what are the options? Well, the other 5, the women can only switch back and forth, and that's the 2 here. And the 3 men can be arranged in 3 different places. And that's 3 factorial. So that's 2 times 3 times 2 times 1, which comes out to be 12. It's a neat question. All right. Question 17 is just NCR and seeing if you can find the button on your calculator and calculate it. Easy peasy, no problem. Question 18. In how many ways can 6 questions be selected out of 10? Do we care what order they are selected? And do we care if the questions are different? Well, to answer the second part first, questions are different. It sounds like we're asking out of 10 unique questions, we're picking up 6. So there's our unique items. But are we caring if we pick first question first and second question second? Or do we just want to get 6 out of 10? If we want to get 6 out of 10, we're picking all of them up at the same time. We're looking at NCR, in our case 10C6, as a solution. Right? If you're picking one at a time, that's NPR. If you're picking a bunch of them at the same time, because you cannot tell which one came first, which one came second, then we're talking about NCR. We're talking about combinations versus permutations. Question 19. How many different committees of 2 men and 3 women can be formed out of 8 men and 9 women? Well, 8 men, we're picking 2. 9 women, we're picking 3. So 8C2 times 9C3. Question 20. Question 20, no restrictions. Well, if there's no restrictions, 7C3 times 9C4 times 6C5 times 8C3 are exactly the reasons as question 18 and 19. B, a particular man and a woman must be selected. If they must be selected, then there's less men to be chosen to the committee, less men to be chosen, and less people we have to choose. So you have a smaller pool and you pick less. And the same thing happens here. Boys stay the same and girls stay the same. Problem 21. Problem 21, in how many ways can a group of 12 people be divided into 7 and 5? Alright, so first thing, we're going to take all those 12 people and we are going to arrange them into a big line. So we're going to get 12 people into 12 unique spaces, and that's 12 factorial. Then what happens? Then we're going to split it up into 7 and 5. Do we care how those 7 people are arranged, and do we care how those 5 people are arranged? No, we care about splitting them up, which means all the 7 people are mixed up, which means we're losing some of the resolution we had here, because remember 12 factorial means 12 unique individuals in 12 unique places. If we divide 12 factorial by 7 factorial, we are saying we don't care how the 7 are arranged. And if we divide it by 5 factorial, means we don't care how the 5 are arranged and the 7 are arranged, which means that we lose the resolution there. Still 12 people, but now those 12 people are in a group of 7, which arrangement we don't care about, and a group of 5, which arrangement we don't care about. And so that's that. Part B says 3 groups. Well, 12 factorial divided by 6 factorial times 4 factorial times 2 factorial. And there is it. Now there are other ways to look at it, but the easiest one is to say, hey, once you pick all of those people into this group of 6, let them mix and don't care about the arrangement, and that's why we divide by 6 factorial. If you never seen this before, I believe in one of the lectures I ask you to make new words from the word statistics. Which has 10 letters, so it's 10 factorial if you arrange. But then we lose 3 factorial for the S's, 3 factorial for the T's, 2 factorial for the I's. Right? Yep. And we do this example in the lecture, I believe. So that's 21. 22. 22 is exactly the same type of questions, just asking about mathematicians and the linguists. No restrictions, so 5c3 times 7c4. B. 2 particular mathematicians must be on the committee. Well, if they must be on the committee, we only have 3 mathematicians to choose from, and we can only choose 1 because 2 of them are already picked, and then 7c4. And then part C, 1 particular linguist cannot be on the committee. Again, that makes our life easier. 5c3 because mathematicians didn't change, times 6c4. We still have to pick 4 linguists, but we only have 6 left because one of them got discarded. Problem 23. Here it is the die toss. The dice toss. And we are looking at find the probability of scoring 8 points in 2 tosses of a pair of fair dice. So we have 2 tosses of a pair. Okay, so we want to score 8 points. So probability of 8 points on 2 dice is what? 4 and 4, that's 1, 3, 5, and 5, 3. So that's 3 out of 36, which is 1 out of 12. Okay. So, to score once. What does it mean score once? Means 1 out of those 2 tosses we have to score this, but the other one we can't. Dice tosses are independent events, which means that tossing the dice once and then tossing the dice again they don't affect each other, which means that we need to have probability of 8, right, times probability of not 8, which is 1 out of 12 times 11 out of 12, which comes out to be 11 out of 144. Right? We tossed 8 once, and we didn't toss an 8. Right? A pair of dice means 2 dice. Okay, so that's A. B. At least once. Well, at least once means 1 probability of what? Of no 8 and no 8. So what is that equal to? Well, that equals to 1 minus probability of not 8, 11 out of 12, times probability of not 8, 11 out of 12. So that equals to 1 minus 121 over 144, which equals to 23 out of 144. Again, at least once, right? At least once means either one or twice, right? To toss 8 once is 1 out of 12. And then not tossing, not tossing again is 11 out of 12, so we get 11 out of 44. The other we would have to consider at least once is twice, tossing 8 twice. Right? All right. Good question. And then part C, toss twice. Well, what is twice? Well, twice means 1 over 12 for the first 8 and 1 over 12 for the second 8, which comes out to 1 out of 44. Cool. Let me check something here. All right. So here's the explanation why we do wanna do at least once this way. Because probability of at least 1/8 means probability of 0, right? Probability of 1, probability of 2. At least 1 means these two, right? This is the 2 not 8s. So probability of 1 and probability of 2. If we look at probability of 2, that's 1 over 144. So let's look at this, probability of 1. Probability of 1 is this. So I toss a 8 and then a not 8, and that comes out to be 11 out of 144. But I could also toss not 8 and then an 8, which would be again 11 out of 144. 11 plus 11 plus 1, 23 out of 144. Right? So this is this, and this is this whole thing is that. Right? So there's a lot more manipulation, because I could 8 not 8, or I could go not 8 and 8. If you got to the binomial distribution formula, that's NCX P to X Q to N minus X. And then there's a lot of dealing with that. Right, that was question 23. Question 24. And we've been doing it for a while now. Almost an hour and a half. All right, question 24. Sorry. Question 24. Two cards are drawn successively from the ordinary decks of cards. Find first card is not a 4 of clubs or a 5. Well, there's an or, right? So we're looking at 1 minus probability of 4 of clubs, 1 out of 52, plus probability of 5, 4 out of 52. So that's 547 out of 52. That's A. B. First card is a king, but the second one is not. Which means we're looking at multiplication. So the first one was addition rule and a complement. The second one is multiplication. So multiplication is what? First one is a king, 4 out of 52. And the second one is not a king. So there's 48 cards left and 51 cards in the deck. So that's 4 times 48 divided by 52 divided by 51. So that comes out to be 16 out of 2 to 1. C. At least one card is a spade. Well, we know what at least one means. Means 1 minus the probability of not having a spade, which is what? How many spades are there? 13, right? So 52 minus 13, there's 39 cards out of 52. And probability that the second card is not a spade, 38 out of 51. So this comes out to be 1 minus 19 over 34. So that comes out to be 15 over 34. Right? Again, not a spade, not a spade, because what I'm looking for is at least one spade. So I'm looking probability of one spade and a probability of two spades combined, where if you have one spade, it could be either the first or the second card. D. The cards are not of the same suit. Well, what does it mean they're not of the same suit? Well, it means that the first card can be anything, and the second card is what? Well, it's some other card from another suit. So how do we write it down? I'm just gonna see if I can find a better solution. So if I was going to go 4 times. would that work better? No, let's do it this way. All right. So we are going to do this. We can pick the first card any way we like, and there's a couple ways to do it. We can say, hey, we're picking any card we like, or I could say I'm picking 1 out of 4 suits and there's 13 cards in that suit, which must follow by picking a card that is not in the suit you picked, which is 39 out of 51. And in this case, it's 39 out of 51, right? Again, 4 out of 13 is 52, so those two are equivalent. But what I'm looking for is the second card, and this is the important part. Just trying to figure out if there's a easier way to explain. Right, so what we're considering is just the second card, because the second card is not in the suit that you picked. Which suit doesn't matter. You take a deck of cards, you pull out a card, and now you have 39 options of cards that don't match that suit, which is this, which after simplification should come out to be 13 over 17. All right, so that's D. E. E is not more than one card is a picture card. Jack, Queen, or King. Right. No more than one. Which means 0 and 1. So the complement is 2. Right? No more than 1 means the complement of it is 2. So what we are looking for, 1 minus the probability of picture and picture. So that's 1 minus probability of a picture. There's 4 queens, 4 kings, 4 jacks. So that's 12 out of 52. And then another picture, that's 11 out of 51. Which comes out 1 minus 11 over 221, which means that the answer is 210 over 221. Again, no more than 1 means 0 or 1. So the complement of it is 2. Why? Because we're only drawing 2 cards. F. F is asking the second card is not a picture card. Well, how many picture cards are there? 12. So what's left? Well, we that's 40 cards, right? Out of 51. Second card is not a picture card. Yes. Well, there's nothing else to it, right? Or did I miss something? Second card is not a picture card. Feels like I missed something. Okay. Scratch that. All right. We're picking first card. If the first card is a picture card, that's 12 out of 52. So the first card got picked, and it's a picture card. That's 12 out of 52. Second one is not a picture card, which means that there is 40 out of 51. But the first card could have been not a picture card, and this is 40 out of 52 times. Second one is not a picture card, it's 39 out of 51. All right, I still got it. So that comes out to be 40 divided by 52 times 51 in parentheses 12 times 39 plus 39. And that's 4051. So this is 51. So 51 divided by 51 cancels out. That's 40 out of 52. And 40 out of 52 comes out to be 10 out of 13. Again, this is the question we did about moving marbles. Question 9. It's the same idea. If the first card was picture card, then the second card, we still have 40 non-picture cards, but we lost one card. Or the first one is a non-picture card, 40 out of 52, times a non-picture card, which is 39 out of 51. And then we do the math and it comes out to 10 out of 13. All right. That's being said. G. 24G. G is second card is not a picture card, given that the first card was a picture card. Well, if first one was a picture card, then the second one, not a picture card, again, the first one, the second one is 40 out of 51. Right? This is this case. There's still 40 non-picture cards, but there's only 51 cards. That's G. And then H. The card are picture cards or space or both. Okay. So first of all, let's do probability of picture or spade. Let's figure out what this is. Well, that probability equals to what? Picture is picture plus probability of spade minus probability of pick spade. Picture is 12 out of 52. Probability of spade is 13 out of 52. And probability of picture spades, there's 3 spades with pictures out of 52. So this comes out to be 22 out of 52. All right. And then the cards, both of them are picture cards or spades or both. So both of them come from this thing. So the first card is 22 out of 52. What's the second one? Well, 21 out of 51. Why? Because we lost one picture or spade card, or both, right? And we lost one card. And that should come out to be 77 over 442. That's how you do H. Problem 25. Problem 25. We have 9 tickets, numbered 1 from 9, inclusive, if 3 tickets are drawn. Okay. Well, so we have two options. Either we go even, odd, even, or we go odd, even, odd. If we go even, odd, even, there's 4 even numbers out of 9, times odd, there's 5 odd numbers left, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. There's 4 even. And odd, there's 5 to begin with, right? So I start with one even, 1 odd, but there's only 8 numbers left, and the last one is even again, so there's 3 out of 7. Plus, again, addition rule, odd, 5 out of 9, even, 4 out of 8, and then odd, 4 out of 7. This cancels out, and that's 20 divided by 5 out of 18. Let's see. So this is 4 times 5 times 3 plus 5 times 4 times 4 divided by 9 times 8 times 7. This is 16. That's a 2. Let's see. 4 times 5 times 3 times. Oh no, hang on. And that's 1/2. Let's do 5 times 3 plus 5 times 4 times 4 divided by 7. Yeah, that comes out to be 5 out of 18. All right, 26. 26. The odds in favor. Odds. So if we have odds of 3 to 2, that doesn't mean 3 out of 2 times. That means that if you play 5 games, A wins 3 out of those 5 and B wins 2 out of those 5. So that's a big complication one might find here. So in case of A, in favor of A winning at least 2 out of 3 games. Well, at least 2 means probability of winning 2 plus probability of winning 3 games, right? And what are the chances A is going to win 3 games? Well, so let's look at the 3. If A wins 3 games, that's 3 out of 5 times 3 out of 5 times 3 out of 5. Right? That's this. Now, if A wins 2 games, 2 out of 3 games, we have to arrange them somehow. So what we're looking at is we're looking at an arrangement 3C2, right? 1, 2 out of 3 games, so we have to arrange them, times what? Well, he won twice, so 3 out of 5 times 3 out of 5, which is the probability of it winning, and lost once, 2 out of 5. And that comes out to be AD 1 out of 125. What's 3C2? This is just 3. So again, in favor of A winning at least 2 games, which means he has to win 2 or 3 games. Probability of winning 2 games is here, probability of winning 3 games is here. If you add them up, you get this. B, so 26B. A losing the first 2 games to B. Which means what? Well, which means B won 2 games, right? So A losing to B. Well, which means A lost. So B won. So that's 2 out of 5 times 2 out of 5. So that's A losing to B is this. Now what is the question saying? It's saying what are the odds against A losing? Well, this is A losing. So against it is this, the complement. And the complement of that, this is 4 out of 25, so this is 21 out of 25. So what would be the odds? Well, the odds would be 21 to 4. That's odds. That's probability. Question 27. An urn contains yellow, blue, 5 marbles are drawn at random without replacement. Find the probability 3 yellow and 2 are blue. Alright, so first of all, how many ways can we satisfy this? Well, out of 7 yellow marbles, we pick 3. Out of 9 blue marbles, we pick 2. So this is all the arrangements that satisfy our need. So now probability means we have to take the conditions that satisfy the probability, divide by all possible arrangements. And there's 16 marbles in the vase, and we're only picking 5. Right, so this is the arrangements that work for us, and this is all possible arrangements. Question 28. 3 cards are drawn from an ordinary deck of 50 cards. Find the probability all cards are of the same suit. Well, there's 4 suits, and in each suit there's 13, and we're picking 3 cards. Right? Because either we can pick all hearts, all spades, or clubs, or all diamonds. Out of what? Well, all the possible cards. Right? This is all combinations of 3 cards you can pull from a deck. This is of 1 suit, and we have 4 suits, so we can do it 4 times. So that's A. B. At least 2 aces are drawn. Okay, well, there's 4 aces, and we're gonna pick 2 of them, right? And what? And then we have to pick all the other cards. So out of the 48 other cards, we have to pick one, right? We're drawing 3 cards. If 2 of them are aces, that's this. Now it says at least 2 aces. So I could be 2 or 3 aces. What's 3 aces? Well, that's out of 4, we picked 3, right? 2 aces or 3 aces. Divided by what? Well, by all the possible arrangements of 3 cards. These things get a little tricky. They just need, well, they require kind of consistency to do it. Problem 29. Find the probability that a bridge player is given 13 cards, of which 9 cards are of one suit. Okay. So, one suit means 13, and we have 9 cards of this. How many suits there are? There are 4 suits, right? And then he needs 4 other cards out of a non-suit. This. Divided out of, well, all the possibility of 13 cards out of 52. Out of curiosity, how big is that number? Oh yeah, the possible combinations of 13 cards out of 52 is 635 billion. So that's that. All right, question 30. How many words can you make with 4 letters if all letters are different? Well, that's 5 letters into 5 different places. That comes out to be 5 factorial. Again, 5 unique words into, 5 unique letters into 5 unique spaces. 5 factorial. So that's part A. Part B. 2 letters are identical. If 2 letters are identical, we still have 5 objects into 5 places, but because we cannot distinguish 2 of them, we lose 2 factorial resolution. I don't know if I told you guys the story of Billy, Bob, and James. This is exactly that. And then question 31. The probability that a man will hit a target is 2/3. If he shoots at the target until he hits it for the first time, find the probability that it will take him 5 shots to hit the target. Okay. Which means what? Which means he missed the first time, he missed the second time, he missed the third time, he missed the 4th time, and he hit the 5th time. Which comes out to be 2 out of 243. And that, ladies and gentlemen, concludes the 31 problems for homework 1. Again, homework 1, just like the homework 2 I'll be posting very shortly, are problems for you to do and get familiar with. Eventually, with enough notice, you will get a homework which has assigned a set of problems. Most of those problems for that homework will come from those homeworks that I gave you. They will be either extremely similar or extremely close to. There might be slight differences. Like, for example, how many words can be made from 6 letters, not 5, right? So it will be 6 factor. So we little differences. So if you have done those homework and you kept your notes, it will make the homework extremely easy for you. On the other hand, if you find this very easy, you're more than welcome to do the homework when the time rolls around. So there will be a small homework for you to do, and I'll grade that. And then the final will come from problems, mostly from problems that look like this. So if you're planning on passing with at least a C, if you know how to do all the home problems that I assigned this semester, you will be smooth sailing for the final. Now, if you want an A, it will require a little bit more work, but I wouldn't worry about it as these problems aren't very difficult, and the rest of the semester is again not computationally heavy. So this is it. Again, this is going to get posted as soon as it finishes uploading to YouTube, and I will be doing my best to answer all the questions now that I have my rig working again, which is exciting. Thank you, and well, good luck.